Okay, so first of all, I'd like to thank the organizers for putting together this wonderful conference and giving me this opportunity. So in this talk, I'd like to talk about non-supersymmetric branes in heterotic string theories. And this talk is mainly based on these works, these two papers, which are collaboration with Justin Kaidi, Kantaro Omori, and Yuji Tachikawa. And I will also mention my own work. And there is also another related work with my students and the postdoc, Masaki Fukuda, Shun Kobayashi, and Kento Watanabe. So in quantum gravity, it is believed that there exist dynamical objects for all possible charges. And one of the reasons for this conjecture is that we can use black holes or black branes to realize such charged objects. For example, in 4 dimensions, we can realize a particle with magnetic charge by using a magnetic black hole solution. And in this talk, I will focus on some generalizations of magnetic charges, which are characterized by topology of gauge fields. So I will consider this kind of situation. So here is a brane, and around the brane, there is some topologically non-trivial gauge field configuration. In general, charges are measured by the behavior of gauge fields at infinity. And so the situation is like this. So, so we can decompose 10 dimensions into p plus 1 dimensions, which are parallel to the p brane, and the radial direction, and the angular sphere. And we can take this angular sphere at infinity, which surrounds the brane. And a generalization of magnetic charge is a topologically non-trivial gauge field configuration on this angular sphere. And it is conjectured that for any given topology at infinity, there exist some branes or some dimensional configurations in the interior region. So this conjecture means that for any given topology at infinity, we can always interpolate that configuration to the interior. So in this talk, I will talk about heterotic superstring theories in 10 dimensions. And the gauge group is either of these two groups, spin 32 over Z2 or E8 cross E8 cross Z2. And the purpose is to study branes characterized by topologically non-trivial gauge field configurations on the sphere surrounding the brane. And it turns out that these branes have very non-trivial properties. And in particular, I will later argue that the world volume theories on these branes are actually non-Lagrangian, non-supersymmetric theories in higher dimensions. So they are very non-trivial. Okay, first, I'd like to discuss the supergravity configurations for these branes. So we can consider this sphere surrounding the brane. And in general, topologies of gauge fields on a sphere for gauge group G are classified by this homotopy group. So if the dimension of the sphere is n, so here this n is 8 minus p in our case. And so if the dimension is n, then the homotopy group is pi n minus 1. And the reason for this classification is that, so on this sphere, we can construct gauge field configurations by gluing gauge field configuration on the northern hemisphere and southern hemisphere, and we can glue them along the equator. Then the transition function along this equator are topologically classified by this homotopy group. So this is the reason for this classification of gauge field configuration on the sphere. And there are 4 non-trivial homotopy groups of these groups in the relevant range of dimensions. So we have this pi 0, pi 1, pi 3, and pi 7. And correspondingly, we get 7 brane, 6 brane, 4 brane, and 0 brane. And in this talk, just for concreteness, I will mainly focus on the case of the Six-brane, but other branes have also similar properties. So some details are different depending on the dimensions, but some qualitative properties are very similar among these branes. And I should also mention that there is some early work on the 0-brane and 4-brane by these authors. Okay, so let's see the Six-brane. So the Six-brane is topologically characterized by this homotopy group, pi1 of spin 32 over Z2. This homotopy group is Z2. So this comes from the division of the group by this Z2. And the corresponding gauge field configuration is a magnetic flux on this two sphere. So this gauge field takes values in the Cartan subalgebra of the gauge group. And so these Qi are parameters. So they are basically magnetic charges. And this epsilon mu is just the volume form on S2. So this Six-brane has a magnetic field around it. And there are two different topological classes. If all Qi, so this parameter Qi, are all integers, then this gauge field corresponds to the trivial element of the homotopy group. So this gauge field configuration is, in this case, topologically trivial, and the brane can decay. On the other hand, if all Qi are half integers, then this gauge field corresponds to the non-trivial element. So this is topologically non-trivial, and the lowest energy configuration is stable. So the stable configuration is that all Qi are 1/2. Okay, now let me show the supergravity configurations for this Six-brane. The supergravity solutions for this Six-brane have been basically obtained a long time ago. So they are explicitly written by Horowitz and Strominger. And also similar solutions for the 4-brane and 0-brane may be possible. This is my another ongoing work. And these solutions are very qualitatively very similar to the solutions of the NS5 branes. And Horowitz and Strominger obtained general solutions, but I will only present the extremal limit. So the extremal Six-brane solution is like this. So in this metric, this x mu are 7-dimensional coordinates which are parallel to the Six-brane, and r is the radial direction, omega 2 is the angular direction, and this r0 is a constant. So this r0 is determined by alpha prime and these magnetic charges Qi. So this is the extremal metric, and also dilaton has a non-trivial dependence on the radial coordinate. So this solution looks like this. So here I'm suppressing the directions parallel to the brane, and I'm just writing the r and omega directions. So far from the brane, we of course have this flat region. And by taking the near horizon limit, we get this slot region. In this slot region, the radius of the sphere is constant. The radius is given by this r0. And the dilaton also has a non-trivial dependence on the radial coordinate. Here, this y is a new radial coordinate. And so this is a linear dilaton configuration. So this slot region may be a holographic dual of the world volume theory of the p-brane. Well, at least that was the interpretation in the case of the NS5 brane. So in the case of the NS5 brane, little string theory is living on the world volume of the NS5 brane, and this slot region is a holographic dual of that little string theory. So similar interpretation should be also possible in our case. Okay, next, I'd like to discuss this exact world sheet theories for the near horizon region or the slot region. In the slot region, so this radius of the angular sphere in the slot region is very small. So its size is of the order of alpha prime if all the magnetic charges are order 1. So in this region, a world sheet analysis to all orders of alpha prime is more appropriate. And first, let's recall the world sheet theory for the flat 10-dimensional space. So in flat 10 dimensions, the string world sheet theory is just given by this theory. And here this group G is either of these groups. And this G1 is the current algebra theory based on this group G at level 1. So this is a familiar world sheet theory for the heterotic string theory. Okay, now I claim that the world sheet theory for the slot region is given by this theory. So in more detail, this R1, P is n equal 1, 0 sigma model with flat target space. So the supersymmetry is 1, 0 because we are considering heterotic string theory. And this R linear dilaton is n equal 1, 0 linear dilaton CFT. And this HK is some current algebra theory with group H and level K. For instance, in the case of the Six-brane, this group H is SU16 over Z4, and the level is 1. So these groups H and the level K are known for all the branes. I don't discuss any detail of the derivation of this slot region, but let me give a very brief sketch. For the derivation, we use some duality of current algebra theories. So this G1 is actually equivalent to a product of current algebra theory, this HK and SO8 minus P at level 1. So this SO8 minus P at level 1 is realized by some Majorana-Weil fermions. So by using this equivalence, we can decompose this 10-dimensional, this world sheet theory for the 10-dimensional space in the following way. So this 10 dimensions may be decomposed into this P plus 1 dimensions and the radial direction and the angular sphere. And the G1, this current algebra theory, is decomposed into HK and this SO8 minus P at level 1. So this is a flat world sheet theory for the flat 10 dimensions. Now we turn on some gauge field configurations on the sphere. And I don't explain the reason, but it turns out that the effect of gauge field configuration on this sphere is such that, so this sphere sigma model and this part of the current algebra theory are actually combined. So they are combined into an n equal 1, 1 sigma multiplet for this sphere target space. Actually, supersymmetry is not enhanced to 1, 1 at the level of interactions, but we believe that the dynamics of this part is at least qualitatively very similar to the dynamics of n equal 1, 1 sigma model. And it is believed that this sigma model is gapped in the IR. So this part disappears in the IR. But we still have to match the total central charge required by string theory. So to match the central charge, this radial direction should become a linear dilaton. So in this way, we get this world sheet theory for the slot region. But I omit the details. Okay, finally, I'd like to discuss a few properties of the world volume theories. And they have very interesting properties related to anomalies. I claim that the world volume theories on the p-branes are very likely to be strongly coupled, and in particular, non-Lagrangian, non-supersymmetric theories in higher dimensions. And this non-Lagrangian nature is suggested by some considerations of massless fermions and anomalies. So let me explain this point. We can regard this angular sphere as an internal space. So we can consider compactification on this angular sphere. Then massless fermions after compactification on this angular sphere are obtained by computing either fermion zero modes on this sphere in supergravity or fermion spectrum using this CFT. So at the level of supergravity, we have topologically non-trivial gauge field configuration on this angular sphere. So we get some zero modes, and these zero modes give massless fermions after compactification. And in the slot region, we have this exact CFT. So we can just use this CFT to compute the fermion spectrum and see the massless fermions. So in either way, we get some massless fermions. And it turns out that these fermions have anomalies under this symmetry H. So we need some Green-Schwarz term to cancel these fermion anomalies. So let's see the case of Six-brane. In the case of the Six-brane, the angular sphere is S2, and we have this magnetic flux. And the commutant of this gauge field in SO32 is SU16. So here I'm neglecting the global structures of gauge groups. So 10-dimensional gauge group is roughly SO32. And the low energy gauge group is SU16. And we have the Green-Schwarz term in 10 dimensions. So here this is a coupling between the B field. This B2 is the B field. And so this B field is coupled to this SO32 gauge field. And after compactification on S2 with this magnetic flux, we get a Green-Schwarz term in 8 dimensions. So this is a coupling between the B field and SU16 gauge field. So this is the situation after dimensional reduction on the angular sphere. And in this figure, I'm regarding this p-brane as a boundary of the radial direction. So in the bulk, we have anomalous fermions and the Green-Schwarz term. So this p-brane must give a boundary condition for these fermions and the B field. And it is very hard to imagine an explicit boundary condition for chiral fermions at the p-brane. So in general, it is very hard to write down any boundary condition for chiral fermions regardless of the anomalies. So this situation is somewhat similar to the situation of Karan-Rubakov problem for some magnetic monopoles. But our case is more difficult because we are in higher dimensions. And moreover, the existence of anomalies suggests that the boundary condition should mix the fermions and the B field. The reason is that, so in general, it is believed that anomalous systems cannot have boundary conditions. So these fermions alone cannot have a boundary, but these fermion anomalies are cancelled by the B field. So the boundary condition should mix the fermions and the B field. So it's really hard to imagine such a boundary condition. So it is very likely to be non-Lagrangian. It is also interesting to consider compactification of the p-brane. And in particular, some further non-trivial properties may be revealed by compactification on S3. So let me discuss this compactification. So we have this, before compactification on S3, we have this situation. So we have this p-brane as a boundary. And in the bulk, we have this Green-Schwarz term. Here, this IP-1 is a Chern-Simons form for the symmetry H. And we also have some massless fermions. Now, we compactify this configuration on S3. And in this S3 compactification, we put n units of the B field flux. Then this p-brane is now compactified on S3. And in the bulk, we get Chern-Simons term. And the flux number n becomes the level of the Chern-Simons term. And this H is a gauge symmetry in the bulk, and it is a global symmetry from the point of view of the brane. So the p-brane compactified on S3 with the B field flux n has a two-fifth anomaly determined by the anomaly inflow from this term. So we have this Chern-Simons term in the bulk, and there's an anomaly inflow from this Chern-Simons term. So this p-brane must have some anomalous degrees of freedom. So we may wonder what is the explicit theory after compactification on S3. And about this compactification, I have this conjecture. So in this conjecture, p-brane compactified on S3 with this n units of the B field flux may be dual to ns5 branes compactified on this 8 minus p dimensional sphere with the gauge field flux, which we are considering. So this gauge field configuration is associated to this homotopy group. For example, in the case of the 6-brane, these ns5 branes are compactified on S2 with this magnetic flux. So let's suppose that this conjecture is true, and even if this conjecture is true, there is some subtlety about some strong coupling effect, but I neglect these subtleties and just compactify ns5 branes very naively. Then after naive compactification of ns5 branes, we get this 4-dimensional theory. So this is the theory obtained after, so this is the theory of the 6-brane compactified on S3 with the B field flux. So we get 4-dimensional SUN gauge theory, and it has SU16 global symmetry, and it has some chiral fermions, 2 times symmetric representation, 2 times anti-symmetric representation, and the bifundamental of SUN times SU16. And these bifundamental fields match the SU16 anomaly, which is required by anomaly inflow. It is really very hard to imagine such a 7-dimensional Lagrangian whose compactification on the odd-dimensional sphere gives 4-dimensional chiral fermions having perturbative two-fifth anomalies. And here, this matter content depends on the duality, but even without assuming the duality, some anomalous degrees of freedom are really required just from anomaly inflow. So that is a very robust prediction. So it's really hard to imagine such a 7-dimensional Lagrangian. So it is very likely to be a non-Lagrangian theory. Okay, let me summarize the talk. So in heterotic superstring theories, there exist some p-branes whose charges are characterized by the topology of gauge fields on the sphere surrounding the brane. And the exact worldsheet theory for the near horizon region, or the slot region, is given by this worldsheet theory, linear dilaton times some current algebra theory. And the world volume theories on the branes may be non-Lagrangian, and they have very mysterious properties related to anomalies and chiral fermions. That's all. Thank you very much.
Thanks for a great talk.
Hi, I have a really elementary question. I'm here. Yeah. So you wrote one of the heterotic gauge groups as E8 times E8 with a semi-direct product of Z2. Mm-hmm. I was wondering where this semi-direct product comes from and how you see this at the level of the allowed vectors on the wet lattice, for example.
So this G2 comes from interchanging this. So there is two E8 groups, and we can interchange them. So that is this G2 symmetry.
Miguel had a question.
Thanks for the nice talk. This is super interesting. So I wanted to ask about the volume theory. Do you expect that it's a field theory, or could it be like a little string theory?
I don't know. I really want to know that, but I don't know. Maybe it's some, similar to the little string. And if we take the low energy limit, it may become a CFT, or even in the low energy limit, it may not be a CFT. I really don't know. So.
Yeah, this was going to be my second question. Do you know if is there any argument that it cannot flow to something free in the deep IR or something like that?
Something free? I mean, so how can I go back? Okay. So anyway, so if this conjecture is true, so it's S3 compactification gives this interacting four-dimensional theory. So I don't think it's free. And we also have to match some anomalies. I mean, if this is a free theory, then it has a Lagrangian description, but I cannot imagine any Lagrangian, seven-dimensional Lagrangian, whose compactification on S3 gives anomalous degrees of freedom in 4 dimensions. So, yeah, I don't think it's a free theory.
Okay, we got more questions here.
I have a comment that the six-brane near-horizon region is not described reliably by supergravity, and also it's not described reliably by an exact worldsheet CFT description, because the string coupling becomes of order 1 in the vicinity of the six-brane. So,
yeah, that's right. So this, here I claim that the holographic dual of the world volume theory is given by this, but it has a problem about this linear dilaton. So the dilaton becomes very large. The same problem happens in the case of NS5 branes, but in that case, there is some way to regularize the strongly coupled region. But actually, in our case, it's more difficult. Actually, some theory of topological modular form gives some obstruction to regularize the strongly coupled region. So our theory is more difficult than NS5 branes. So yeah, thank you very much for the comment.
Okay. Any more questions? Yes.
Thanks for the nice talk. Yeah, so my question's kind of similar to the previous comment. So can you comment on how well you know these branes are stable or not? I mean, given that you have this region where the string coupling becomes large.
I mean, so what I can say is that, so this is, this has a topologically non-trivial charge. And that can be measured at spatial infinity. So that charge must be preserved. And then there must be some configurations, but I think the only possibility is to have some branes.
Well, I guess there's a possibility that it could, of course, spread out, of course, and become infinitely dilute. Kind of like the type 1 non-BBSD7 brane does this. Even though
Type
it has,
1
it does, yeah, the type 1 non-BPSD7 brane, it has
no,
a
no, no.
conserved
Type
charge.
1 non-BPS brane cannot explain this. It's more exotic.
Okay, yeah, I just was giving an example, like a brane with a conserved charge that's not stable. That's all. Anyway.
I believe this 6-brane is stable, but yeah, I don't have a proof, but yeah.
Okay. I think just two more questions, Mahab.
Well, about type 1, so there is a duality, or there's supposed to be a duality between SO32 heterotic string and type 1. So you seem to be suggesting, in particular, that there is a new configuration in type 1 theory. Have you thought about this?
There's a new configuration in type 1, yeah.
And the point is that where the dilaton is of course determining the coupling, and it's becoming infinite. So you're actually going to a type 1 description. So I was wondering whether you have thought about trying to look at for a type 1 description, which might be actually much easier.
Actually, I'm not sure, but type 1 description may not be so simple. So dilaton becomes very weakly coupled, but instead we have some singularity in the, I mean, the curvature of space-time becomes very singular. So it's difficult even in type 1.
Okay. Well, yeah, maybe we can continue this after the session. Let's thank Kazuya again.